Good afternoon, everyone, and welcome to this session on the business impact of code quality. And this is a broad topic, and I want us to approach this topic from the perspective of technical debt. So technical debt is something that I think most of you are familiar with. And we as organizations, we take on technical debt when we try to deliver a feature quicker by compromising code quality. Or maybe our understanding of a particular business problem shifts so that our design is no longer a good fit. Or maybe, just maybe, our design wasn't a good fit to start with. Whatever the root cause, the end result is the same. We end up with code that's more expensive to maintain than it has to be. And that's the definition of technical debt that I'm going to use throughout this talk. Now, over the past years, there has been some pretty interesting research on technical debt. Some research that has actually quantified the costs of technical debt. And I have to tell you, it's a pretty depressing read. Because depending on what papers you look at, it turns out that technical debt wastes up to 23 to 42% of developers' times. So that's a lot of waste, isn't it? And to try to quantify that to you and put it into perspective, let's say that we indeed have a 42% waste, right? We're wasting 42% of our time. So let's say that we have 100 developers in our organization. With a 42% waste, we would get the equivalent output of just 58 people. Does that sound like a good deal to you? The thing is that the actual waste is probably even larger, because there's a significant coordination and communication overhead of having 100 people as opposed to just 58. So the waste due to technical debt is very real. But it also goes beyond a financial impact. Other researchers look at security vulnerabilities, and it turns out that there is a very statistically significant correlation between certain software vulnerabilities and code smells, like Bring classes and complex implementations, things that we're going to look at in a couple of minutes. So given what I just told you, that technical debt comes with a huge financial impact as well as this whole security dimension, you would expect technical debt to be really, really high on any decision maker's agenda, right? Is that what's happening? It turns out that other research, again, forces that quite the opposite is going on. A lot of our developers are forced to introduce new technical debt. And the reason we are forced to do that is because companies will constantly keep trading code quality for short-term quick gains like new features. And I've been thinking about this for years. Why is this happening? Why are we making these trade-offs, these short-term trade-offs? I like to think that it mainly comes down to a difference in feedback timing. Because if we think about it, the moment we put a new feature in the hands of our users, we get a quick reward, right? We get immediate feedback. Maybe we win a particular contract, or at least we get a happy user. So the short-term feedback is very quick from adding new features. However, technical debt is a feedback loop that's going to play out over time. And I like to think that this difference in feedback timing, it's like an open invitation to something that psychologists know as hyperbolic discounting. So let me check with you. How many of you are familiar with hyperbolic discounting? Not so many, none of you. That's good. I have something new for you today. Great. So hyperbolic discounting, it's a decision-making bias, and it's something that happens when we humans, when we make choices today that our future selves are going to regret. That's hyperbolic discounting. And hyperbolic discounting is often used in the field of, in the psychology of addiction, right, to explain different addictions. It's also, coincidentally, the best description I have found of why we as companies make such a poor job at managing technical debt. Because just like the addict, we keep trading our future or maintainable code base for the lure of quick fixes and short-term rewards. And once we notice the symptoms, it might already be too late. Or, to put it in the words of Mel Conway, somehow there never seems to be enough time to do something right, but we always find time to do it over and over and over again. So how can we change this game? How can we fight hyperbolic discounting? To me, one of the main challenges with talking about code quality at all is that code is a very abstract thing, right? And software as such is a very abstract concept. And that simply means that I cannot take a code base, I cannot pick it up, I cannot turn it around and inspect it for quality flaws, right? It lacks visibility. So to me, understanding code quality at all starts with visibility. So what I want us to do now is to look into different ways of visualizing code quality to make it tangible. And as a starting point, I would like us to spend a couple of minutes on discussing what code quality actually is. Is there even such a thing? What is code quality at all? And I do hope I have an answer for you, otherwise it will be a very short talk. So I have to admit that I personally dislike the word code quality because it kind of suggests an absolute, whereas reality, it's much more complicated. Code quality is a very multifaceted concept. And I think that's very well captured in the following piece of research. It's an old paper, but it's a paper that had a huge influence on how I look at software. And in the first paragraph here, this paper claims that these different views, these fundamental different views of code complexity, they simply cannot be measured by a single number. There is no such thing. Instead, what I have done is taken a lot of inspiration from the second paragraph here, that a much more promising approach is to identify separate attributes of code complexity, measure these separately, and then combine them. So over the past 5 years, I've been working on a concept that I call code health. And I would like to walk you through it, and then we're going to look at a bunch of case studies. So first of all, how does it work? Well, code health is something that you measure from the source code. So you take the source code and you parse it. And then you look for these specific attributes of code complexity. And these specific attributes, they come in different categories. First, I start to look at the module level. So at the module level, we find a bunch of different code smells, and I'm just giving you a couple of examples here from each category. But the classic is low cohesion. So how many of you are familiar with cohesion? So like, oh, good. Like 2/3 of the audience, perfect. So low cohesion in particular, what that means is very often that you have many responsibilities. So you have multiple business features and rules that you have kind of squeezed into the same class or the same module. And low cohesion is a problem because it makes it hard to reason about the code. When I'm trying to understand a module with low cohesion, I need to understand multiple different business areas, right? I need to understand multiple domain concepts. Low cohesion is also a problem from a correctness perspective, because with low cohesion, you open up the risk of unexpected feature interactions, and those are some of the worst bugs that you can ever have, right? But of course, even if low cohesion is problematic, there are always different levels to code smell hell, right? Because you can always have something like a brain class. So brain class is a module that not only is it low on cohesion, it's also a very large class. And it contains something called a brain method. So brain method is a function level issue. Brain methods are also known as gut functions, right? So these two are synonymous. And a brain method, we've probably all seen them, right? A brain method is this ridiculously large and complicated function, right? Lots of complicated logic inside it. It's a large method, and it tends to be central to its module, meaning that each time you want to change a responsibility in that module, you end up in the brain method, and over time it becomes more and more complicated, right? Then of course you have at the function level, you have classics like copy-pasted code, right? The mother of all reuse. We've all seen it. And at the implementation level, we look at different types of complexity issues. And one pattern that I want to bring up in particular is what's called deeply nested logic. So what's that? Well, deeply nested logic is when you have if statements inside other if statements, and then maybe a for loop for good measure, right? The problem with deeply nested logic is that there has been some pretty good research on large-scale systems, And that research found out that a construct like deeply nested logic is responsible for roughly 20% of all programming mistakes, right? And that's good to know because deeply nested logic is also fairly easy to refactor. So anyway, just to give you a couple of ideas what's included in the code health concept, it's an aggregated metric. So you basically measure all these different attributes, and then you combine them, you score them, and you normalize them into 3 different categories. And that means that we can now classify every single piece of source code as being either green, yellow, or red. And green, that's healthy code. That's the kind of code we want to have most of. And healthy code doesn't mean it's perfect, but it means that the code is easy to understand for a human, for a developer, from the cognitive perspective. So if I, as a developer, pick up a piece of green code, I will be able to understand that code and I will be able to make changes to it safely with low risk. Then we have yellow code. And yellow code, it's like the warning space. So this is where the code has started to take on some technical depth. And we need to be really, really careful here, because if we're not careful, we might end up in the red category. And red code is code with severe maintenance issues and risks. And that's what I want us to look at and try to quantify a little bit further down the road here. All right, enough with theory. Let's see this in action on some real-world open source. So the code base I want to demonstrate on here is Ethereum. Ethereum is a decentralized open source blockchain implementation. And what you see on screen here is code health visualization over the whole code base. So what you see are roughly 50 different Git repositories, 600,000 lines of code. And the way you read this visualization is that if you look at these large circles, the one that I'm hovering over right now, each one of those circles represents a top-level repository. Or if this was a single Git repo, it would be like the top-level folder. So that means if this was one of your code bases, you would recognize the names of these large circles as important subsystems or high-level components. It's also an interactive visualization, so I can click and I can zoom in to any level of detail that I'm interested in. And once I get here to the lowest level of detail, I see that each file with source code is visualized as a circle. And you see that these circles, they have different size. That's because size is used to reflect the number of lines of code. So the larger the module, the larger the radius of the circle. The important thing here is the color, which reflects the 3 different code health categories. So here we see an example where we have 2 pieces of green code and 1 instance of red code that we know is problematic. In general, I'm a very big fan of visualizing things because visualizations have this property that they tap into one of the most powerful pattern detectors that we have in the known universe, the human brain. And that means that by visualizing our code quality, we can very quickly determine where the strong parts are and where the weak parts are, as well as how deep any potential problems go. So I wanted to give you an example here from 2 well-known open source projects. So if you look to the right, let's start from the left. If we look to the left, you see that we have a visualization of React, a well-known JavaScript library that I think a lot of you are actually using right now to building your products. And we see here in React that it seems to be plenty of green code. There's also lots of yellow code. And then what would worry me a bit is that the package that I'm hovering over, React Reconciler, we see that there's like a cluster of red code there. So if this was one of my code bases, then this would be really important information for me to know that, okay, we have a piece of code here where we have to be extra careful. However, we can compare this to Core CLR, the code base visualized to the right. And let me first point out that Core CLR, it's the runtime for .NET from Microsoft. It's a massive code base. So what you see on screen here is more than 8 million lines of code. So it's a lot of code, right? What do we think about the code health? Yeah, well, we see this cluster of red modules, right? It almost looks like, you know, like a bacteria culture, like a petri dish gone mad or something, right? But it's not. It's simply a lot of potentially problematic code. And if I compare this to instances, I immediately see that, okay, Core CLR is going to be more challenging to get back on track. So towards the end of this session, I'm going to return to this particular case study and see what we can do in the instance where we find a lot of red code. But before I do that, I have to kind of deliver on the promise of this talk and connect code quality to a business impact. Because without the business impact, any metrics that we have, they are basically just vanity metrics. And I find it interesting with code quality because I've been working within the industry for almost 3 decades now. And virtually everyone I met has agreed that code quality is important. And yet no one ever had any data to support that statement. So what I would like us to do is to move away from knowing that code quality is important to actually knowing as supported by research. So last year, me and a colleague, Mr. Marcus Borg from Lund University, we picked up this challenge to try to study a relationship between code quality and a business outcome. And the way we did it was by collecting data from lots of commercial code bases. We collaborated with 49 companies that gave us access to their source code, meaning we could measure the code health of every single module that they had, and there were lots of different modules. We also made sure to include companies from several different industry segments. So everything from data science to retailing to logistics, because we wanted to make sure that the findings aren't specific to a domain or industry, that they actually generalize. And for the very same reason, we included data from 14 different programming languages, right? So that we can say with confidence that, okay, these are actually general findings on what happens to code. What we also did was that we connected to their Jira instances. Because by connecting to Jira and similar product management tools, we could actually figure out by taking data from Jira, I'm going to show you how on the next slide, and breaking it down together with version control data, we could actually figure out how long do we as developers spend on implementing a specific feature in every single module. And since we have Jira data, we could also fetch information on what type of work is being done. Are we working mainly on new features, or is it a lot of bug fixes in particular parts of the code? So what we ended up with was basically a large data set, thousands of modules, where every single module contained the code health score, green, yellow, red, information about how long we needed to implement new features, as well as information on the number of defects in that particular module. Does that make sense so far? Yes. Perfect, you seem very much aligned with this. So let's move on. Before I show you the results, I want to explain a little bit about time and development. And I promise you, this is going to be my most tricky slide, but I'm going to try to keep it high level because I do think it's important that we all understand what's being shown here. So how do we know the time in development for a particular module? Basically the time to market, how do we know that? Well, what we wanted to avoid was to add some painful administrative overhead to the development teams, right? We don't want them to have to report it in the Jira instance. So what we did instead was that we used an algorithm that pieced together the Jira data with version control data. And this is how it works. What we did here was that the moment you as a developer pick a task in Jira and you move it to an in progress state, then we start the clock. Then you write some code, and when you do the first commit referencing that particular Jira task, then we stop the clock. And if you're done with the feature, then your time in development is the time between a task moving to in progress until the first commit. Simple. Except that reality is rarely that simple. So occasionally you have to do multiple commits. And what happens then is that we simply continue to count. So, okay, what's the time from the first commit until the next commit? And then you do a third commit. So we kind of continue like that, calculating different cycle times. And at the end, we just sum them up at the file level. So we now know the time spent on implementing a feature down to a file level. And this is what we used for the purpose of this study. So with that covered, what did we actually find out? Does code quality matter? Well, let's have a look. The first thing we looked at was speed to market. And what we found here is kind of interesting. Because what we figured out was that green code is more than twice as quick as red code. So what does that mean to a business? Well, it simply means that if we implement a new capability in one of our code bases and we have red code, and it takes us 2.5 months to do that, then our competitors with green code bases, they can get the same feature in less than 1 month if they have green code. And that means it's going to be really, really hard for a business to keep up with their competitors. So after all these years I spent in the software industry, I have to admit that this is pretty much what I expected. I didn't know the precise ratios, but I did expect a significant difference between red and green code. What I didn't expect was the next thing we looked at. And what we did next was that instead of looking at averages, like what's the average time to implement something, we looked at the variation. What's the maximum time a particular feature can take in red versus green code? And what we found here is quite dramatic, because it turns out that green code is fairly predictable, meaning that each feature I work on takes roughly the same time. It's a time that's close to the average for that module. Whereas the same relationship simply doesn't hold for red code. Red code comes with a lot of variation, and a feature can take up to 9 times longer. So that's almost an order of magnitude. What does that actually mean to a business? Well, I like to think about this variation as uncertainty. And let me assure you that within the software industry, no one, really no one, enjoys uncertainty. I happen to work as a CTO these days, and uncertainty is something I strongly dislike, because uncertainty makes me look bad. So maybe I promise something to a client or to our sales organization that, yeah, you will have this feature in a month. But if we have red code and it takes me 9 months to deliver on that promise, I'm going to look really bad and I'm going to have a lot of disappointed people on the other side. If I instead take on my developer hat, I also dislike uncertainty, because uncertainty is what's causing me stress, overtime, and missed deadlines. Now, finally, the last thing we looked at was that, remember that we collected information on whether a particular Jira task was a bug fix or a new feature. That made it possible to see, is there a relationship between code quality and defects? And what we found here was that red code has on average 15 times more defects than green code. And this is something I would like to say translates into, from a business perspective, this is something that translates into the product maturity experience, right? If we continuously deliver 15 times more defects than we have to do, then we're going to have some pretty disappointed users on the other end. But there's another problem with red code and defects too. Because what happens to all those defects? Well, it's like in the Stephen King movies. Sometimes they come back, right? And they come back in the shape of unplanned work. That means work we didn't anticipate, that work that we didn't have on the roadmap. And now suddenly, instead of doing the next cool innovation or the next cool feature, we are back at fixing bugs that could have been prevented in the first place. So we have the correctness perspective here as well. But that was the business impact. What's the impact on us as developers? After all, I guess you could make the argument that with technical debt wasting 42% of our time, that simply means that we as developers, we can become even more in demand, right? And we can use that to push up our salaries. So maybe technical debt is a developer's best friend. What about that? No, let me tell you that no developer likes technical debt. And I can say that with confidence because I read this book a couple of months ago. It's an excellent read called Rethinking Productivity in Software Engineering. It's a collection of research papers. And there's one study in particular that I found extremely interesting. And that's a study that looked at developer happiness. And the reason they looked at developer happiness is because a happy developer also happens to be a productive developer. I mean, who knew, right? And what's so interesting with this study is that they actually list the top 3 reasons that we developers become unhappy. And I would like to claim that all 3 reasons are possible to connect directly to the code quality results that we just looked at. So the 3 top reasons for unhappiness is, first of all, we developers, we dislike when being stuck in problem solving, right? And you can very easily see how the research I just presented connects to that. So let's say that you attend one of your daily stand-ups, and someone tells you that, yeah, we had this bug here in production, something doesn't quite work out. And you volunteer to fix that because you're familiar with the problem, you're familiar with that area. So you say, okay, I'm going to fix this. I can do it this morning, it's going to be quick. But then you end up in red code. And suddenly you have this huge uncertainty right in task completion. And that means that what you think is going to take 3 hours ends up taking 2 weeks. And it's very clear how that puts us under time pressure, right? And it's also probably going to put the organization under time pressure. And finally, number 3, there's this absolutely wonderful quote from that paper that says that we developers, we suffer tremendously when we have to work with code, with bad code that could have been avoided in the first place. So technical debt and bad code quality is something that's not only impacting the financial side, the security side, it's actually also impacting the happiness and well-being of development organizations. Now, a couple of use cases. Because if we know about this relationship between code quality and the business outcome, how can we use that in our daily work? So what I'd like to share with you is a couple of things that have worked well for me. The first one that I think is really, really important is that code quality, as we have seen, constrains a business. And what we can do with this data is that we can let non-technical stakeholders, people like business managers, product people that don't write code themselves, we can let them have a shared understanding of where are the risks in our code base. And that makes it so much easier to balance improvements versus new features because we can now have a conversation in terms of risk. These visualizations also work as a way of fighting hyperbolic discounting. Because the way you fight hyperbolic discounting, remember the decision-making bias, is by discussing the future risks. Because the moment you start to discuss future risk with your decision makers, you're also priming them to think about how those risks could be avoided. So this is a way of being a bit more proactive. Finally, what I like the most with being able to quantify the business impact of code quality is that refactoring and large-scale improvements can now actually come with a business expectation. We can now actually have this conversation that, yeah, we have this red code over here. It turns out that they have a lot of stuff on the roadmap that's going to touch that area. If we could invest time into improving that code, that red code, and turning it green, then we can expect to be at least twice as quick on average when we implement new features there, and we would significantly reduce our uncertainty and bugs in the process. So I think this can really, really help facilitate both trust and communication between engineering, where I've been working most of my career, and management. Now, the last thing I want to talk about today is that I promised to kind of get back to this scenario where we have a large amount of technical debt, we have a large amount of red code. How do we deal with that? So let's return to core CLR. Massive code base, 8 million lines of code, and lots of it is red. If you look a little bit deeper at this code, you see that most of it is C++. And it's C++ that looks like this. So how many of you are C++ developers? So a couple, like maybe 6, 7 people. Cool. You know, I used to be a C++ developer myself. I did C++ for 10 years. I enjoyed it. But I do remain convinced that C++ is probably the most complicated human artifact ever produced. And I'm also not particularly jealous at the archaeologists of the future that have to decipher this, right? It's going to be a harder nut to crack than the hieroglyphs, I promise you. But anyway, for our purposes, what I mean with that is that if we have, like, look at the red code and the total amount of code is 8 million, we probably have like 2-3 million lines of red code here that looks like that. How are we possibly going to improve this situation? I mean, what we cannot do is to just say, okay, we're not going to do any new feature development for 3 years. We're going to spend 3 years refactoring that part of the code. Right? We would be out of business. We would be Netscape. So we need to do something different. And that something different is a technique called hotspots. So hotspots is something that you cannot measure from code. Hotspots is a behavioral code analysis technique. So here's how it works. As you see here to your right, we have the same type of visualization, but now the color carries a different meaning. The color reflects the change frequency of the code. So what's that? Well, change frequency is simply the number of changes measured as the number of commits that modified that piece of code. So hotspots is something that you measure by connecting to your Git repositories and looking at the change frequencies of each piece of code. And what's so interesting with hotspots is that they give us this window to prioritize. I like to say that hotspots deliver a positive message, because hotspots basically tell us that no, we don't have to fix all our technical debt. And I know that that's a potentially controversial statement, so let me support it by data. Please have a look at the following graph. This might be the most important piece of information that I'm going to show you today. So what you see here is that on the x-axis, you have each file in the core CLR codebase. And these files are sorted to the change frequency. That is, how many commits have you done to each file. And the number of commits is what you see on the y-axis. And as you see here, this distribution forms a power law shape, right? A Pareto distribution. And what that means is that most of your code is going to be in the long tail. That means that it's code that's rarely, if ever, touched. And that's the kind of code where you can actually safely live with a certain degree of technical debt. You can live with some red code in the long tail. You want to be aware of it because it can be a future risk, but it's most likely not urgent. On the other hand, we see that most development activity is at the head of the curve, in a pretty small section of the code base. And this is the section that hotspots help us identify. And this is the part of the code where even a minor amount of technical debt, even a minor amount, even yellow code, can quickly become really, really expensive due to the high change frequency. So let's return to core CLR and see what the hotspots actually look like in the real code base. As you see here, hotspots rarely make up more than 2-3% of the total code base. So using this technique, I can quickly identify the parts of the code where I really need to attend to improvements, right? And look for any overlap with code health issues. And if I have those, then I know that this is high interest technical debt that I really need to prioritize. But I also see that a lot of the code is stable. And stable code is good code. In terms of technical debt, it's low interest technical debt. It's virtually like a free technical debt loan. So drawing this separation is really, really important. And what you have seen today is that being aware of technical debt kind of starts with exploring the code quality dimension. Because that way we can figure out, do we have a problem or not? However, that data alone is not enough to actively manage technical debt, because technical debt simply cannot be measured from code alone. So that's why we need the hotspots to find the impact, to find the relevance dimension, so that we can prioritize and get actionable findings. Now, over these 25 years that I worked in the software industry, I had so many people that have told me, no, we don't have time. We don't have time to refactor. We don't have time to write automated tests. We don't have time to do a proper design. And there seems to be this perception that speed and quality are mutually exclusive. There's like it's a trade-off, right? You can have one, but never both. However, what we found in the Code Red research is that it simply doesn't appear to be true. There doesn't seem to be any such trade-off. Quite the opposite seems to be true. What all this data suggests is that we need quality if we want to be able to go fast. And I hope that this research can help us all turn code quality into the business concern it should be. And now, a couple of references in case you want to dive deeper into this topic. What you see here is a link to the research paper on Code Red. We can read up on all the data and all the details. And then there's also a white paper if you want a higher level summary of the findings. The tool that I've been using for all this research and for visualizations is CodeScene. So if you're curious how this is going to look at your own code, please check it out and consider to support it. And finally, if you want to dive into hotspots and all this behavioral code analysis, then I have a whole book about it called Software and X-Rays. Now, before I leave time for questions, I really want to take this opportunity and say thanks a lot for listening to me, and may the code be with you. Thank you.